So again, creep is defined as the long-term deformation caused by the application of loads for long periods of times, usually for years. It happens for a very long period of time. And creep strain occurs due to sustaining the same load with respect to time. So you know that sustained loads are always the dead loads, and superimposed loads are considered as sustained load because that is not going to change, that is going to always act. In addition to that, a fraction of live load is also considered as sustained load. Now, the deformation that is caused by creep can be divided into two parts. The first is called as elastic deformation, that is going to happen right after the application of loads. And the second one, because of this is basically deformation that is happening short-term deflection. So, because of this load, let's say this girder is going to deflect like this. This is only because of short-term deflection. So, if you write like this, let's say delta S, which is your short-term deflection. So, but if the load remains constant, delta also should remain constant. That is what you must have studied in your structural analysis. However, the delta S will keep increasing. So that is because of the effect of your creep, which is called as time dependent effect, which is the creep deformation. So here, if you measure this delta, which is going to be much greater than your short term deflection, which is delta S, that we need to account for it. Otherwise, your serviceability limits may not be satisfied. This is more so important when you have a long span elements like in bridges. We need to absolutely consider this effect. Right. So schematically again, what is the effect of creep? How is it varying? So now when I start, let's say I take a cylinder, okay, and then I apply load, and then I try to measure the strain. Okay. So now we know that right after I apply this load, let's say I'm applying a load of P. Okay, you know the cross section area of the cylinder. So right after application of strain, so this is your elastic deformation or strain due to applied load. If I keep this P constant, again the strain will not remain constant because of this creep. The strain will keep on increasing. That increase will be initially it will be much higher, then it will gradually slow down, and then it will reach a more or less a plateau value. Right? Again, why is this happening? We have seen. Okay, usually we use water cement ratios. Water more than that is adequate for complete hydration, so that whatever the water that is unutilized in the hydration process, that is going to be sitting in this gel pore and capillary pore as well as between the CHH layers. So when you have a constant load, what will happen is the particles will readjust, and then the water will try to escape from the system, and the CSH particles will try to readjust. Because of that, there will be some additional strain. Okay, so that happens for a very long period of time. So when you start removing the load, again you will recover some strain, which is called as elastic recovery. Okay, and then you may also recover some part of the creep strain that you have accumulated. Okay, like this. However, you may not be able to recover all the strain. So you will be left with some permanent or residual deformation. Okay. Now again, what is the significance of this? If you go back from your stress strain curve for concrete, let's say I have this is your stress strain curve for concrete. Let's say FC and epsilon C. Now what I have done is I have applied this kind of strain, constant stress, and then the initial strain is, let's say, this epsilon instantaneous. Now what we are saying is the stress remains constant, the strain is keep increasing. So strain is basically keep increasing. Now for the same stress, now what is the strain? This is the strain. So if what happens to your secant modulus, the secant modulus now it is going to be this, right? So this is your stress and this is your total strain. Okay, so now what is happening is the elastic modulus EC, right, which is nothing but your FC by epsilon C. Now the epsilon C has increased because of creep. So what happens then? The elastic modulus, there is a reduction. So that is what we have to account, because you know that the deflections are always function of your flexural rigidity, right? EI. So when the E is reducing, your deflections are going to increase. That we need to account for it. Right? So now let us see what are the factors that actually affect the creep. And we said the major culprit is your the cement paste with more water that is not utilized in the hydration process. So if you are able to cure the concrete well, then lesser will be the creep. Okay. Again, sometimes steam curing also reduces this creep. Okay. So these are different types of curing process. You can use gunny bag or you can use steam curing. So if you cure it well, then the lesser will be the creep. Now, usually we use high strength concrete by reducing or using lower water cement ratio, and for workability, we start using chemical admixtures like high range water reducers. So, because I'm having low water cement ratio, there is less water that is going to be available in the gel pore and the capillary pore and between the CSH gels. So, you're going to have a less creep. So usually high strength concrete is expected to have smaller creep than the normal strength concrete because we are making an assumption that I'm going to get high strength concrete by using lower water cement ratio. Again, with creep also increases with increase in temperature that we need to take into account. And again, higher the humidity. What is humidity? Humidity is the percentage of moisture in your air, right? If the air is already saturated with moisture, then it will not be able to absorb the water that is escaping from your concrete system. So less will be your pore water that can escape from concrete. So you will have less creep. So in humid regions, it is expected to have lesser creep. Then again the majority of this creep deformation that is happening because of deformation that is happening in the cement paste. So if your concrete is having high content of cement paste, and again it is expected to have more creep. In fact, if you have a very stiff aggregate and large volume of aggregate, it will help to reduce the amount of creep. Okay. So again, the addition of reinforcing bars in compression also, it is going to help in reducing this creep. Now, another important factor is large members with large volume to surface area have less tendency to creep. Or in other words, for a constant volume, if I am having, let's say, more surface area, then you will have, or uh, for a constant volume, if your surface area is, let's say, it is increasing, then the creep will go because now you have more surface area through which your moisture or water can escape from the system. So that will lead to more creep. Now here we are dealing in terms of volume by surface area. So that is why when you have higher volume to surface area, then you will have less tendency to creep. It is the inverse. Right. So how does the code adjust? As we have discussed previously, at constant stress, strain is increasing. So if I take the secant modulus, the secant modulus is going to reduce. So codes usually gives to take into account by something called creep coefficient. And for example, if you look at IS 456, the code gives you some creep coefficient as a function of your age of concrete at which it is loaded. Okay. For example, if I'm loading the specimen at 7 days, that means that it's still the concrete has not really attained its strength, and there is a lot of water that is unutilized in the hydration process that is available at the time of loading. More is a possibility of escape of this moisture from the system, so your creep effects are going to be more. So the code is saying that in that case you are going to use creep coefficient of 2.2. But if you start loading the system at 1 year where you have completely hydrated the cement, and the availability of unutilized water in the hydration is going to be less. So the creep effects are going to be less. So that is why the code is saying you use a coefficient of 1.1. So what we use with theta is you use it in. So for example, what is it? If I am loading at 7 days, my EC reduces by 1 plus 2.2, which is, so that means almost I am reducing the elastic modulus by 1/3. So you can imagine the deflections will increase by 3 times. So that is we have to account. So in this way, by using reduced effective modulus, the code accounts for increase or helps the design engineers to do the calculation. So deflection estimation will be higher. Okay. So we will study how these calculations are done when we deal with the module on limit state of serviceability. Right. Now we'll go into discuss the other important phenomena that affects the concrete in long term, which is shrinkage. Okay. And shrinkage, as you know, shrinkage of concrete is defined as the reduction in volume of concrete due to loss of moisture. Again, this creep, shrinkage, and relaxation in case of steel, they are all interrelated, but we try to deal it one at a time, and then we study these effects. In fact, if you do incremental analysis, you can consider this effect in increments as well. For now, let's look at it. What is the effect of each one of them in an independent manner? So this is what happens. So shrinkage again of concrete is primarily caused by the drying process, and it is actually resisted by stiffness of the concrete. So again, in concrete, the stiffness is given by aggregate which are stronger and stiffer, at least for low strength concrete. So if you have a good quality high stiff aggregate, again the shrinkage will be reduced. So again, the factors that whatever we discuss that affect the creep is also going to affect this shrinkage, right? So if you can see this example, let's say I take this concrete block, okay, and if there is not going to have any restraint at like what we have seen, then it is going to shrink uniformly and you're not going to develop cracks. Only when your concrete blocks are restrained from shrinking, restraint means you are preventing that uniform shrinkage. So whenever I prevent something to happen, you develop some reaction. So when I prevent this shrinkage, concrete develops tension. That is why you end up these kind of cracks. That happens because you have restrained shrinkage. When you have free shrinkage, everything is shrinking uniformly. There is no problem. But in reality, all the structural members are interconnected. You will always have restraints. So that is why when concrete tries to shrink, the other connecting elements will not allow it to shrink freely, then it will develop restraint and you will develop tensile stresses. Okay, and so shrinkage strains are also actually independent of the stress conditions in the concrete. Okay, so even if there is no load, the concrete can undergo shrinkage and it can develop strain, it can develop cracks. Okay, and shrinkage is also reversible to a great extent. That means if I start doing this alternate drying and wetting, it will cause alternate volume changes in your concrete. So that we need to consider. So this is how the shrinkages is going to change for a period of time. Again, shrinkage will be happening more in the initial time, and then gradually it will reduce and it will plateau over a period of time. Now let's see what is the effect of shrinkage. Again, to prevent shrinkage, usually what we do is these kind of joints. We cut the joint, saw joint. We saw the joint, especially you must have seen in this industrial floors. You know what after concreting flooring is done, usually they'll create artificial small cut basically to accommodate this shrinkage. Okay, and usually that's where the crack will extend. Or if you want to reduce the effect of shrinkage, you have to put this kind of expansion joint. So these are all expansion joint. Okay, expansion joint. Okay, so this we have to consider. And because of this, most of the shrinkage, as we have explained, it happens at a very early age. This is the early age shrinkage crack that what we are seeing in the slabs. Okay, you can see this kind of cracks. This is early age shrinkage crack that has happened on a slab on grade. Now, how does IS 456 consider the shrinkage? Again, the code gives a value of 0.0003, class 6.241. It says that this is the value that you can consider in your design to account for the shrinkages. And now, if you go back to concrete, what is the peak strain? Let's say for a 30 megapascal concrete, you must have seen that as per the IS code, it is 0.0035. Okay, so you can see shrinkage strain is roughly 1/10 is what it is suggested. It's a very small strain. However, when you're dealing with the long members, when you multiply the small strain by a length, then the deformations are going to be significant. So you have to, though the value looks to be small, but the effects can be significant. Again, so the total shrinkage of concrete depends upon the constituents of concrete, size of the member, and what are the environmental conditions that that particular concrete is subjected to, right? For a particular humidity and temperature, the total shrinkage of concrete is mainly influenced by the amount of water present in the concrete at the time of mixing, and it is not really depend upon how much amount of cement. It is basically, it depends only upon what is the amount of water that is available in the system at the time of mixing, and how much it has been utilized in the hydration process, how much it is unutilized in the hydration. So if you have higher water that is unutilized in hydration, you are going to have more shrinkage and more creep. For example, AC allows 0.0008. They have taken a higher value for shrinkage, maybe because of the temperature differences, or can be quite significant. Okay, we talked about this. We have two types of shrinkages. We briefly talked about in the very beginning of the this module: autogenous shrinkage and drain shrinkage. So if you see here, you have drain shrinkage, which is written as epsilon CD, and autogenous shrinkage, which is epsilon C. So drain shrinkage, we know this is because of water loss that is happening to the environment. Now this autogenous shrinkage is because of the chemical reaction between the cement and water, and that because of that the water will be lost from the gel pores and capillary pores. Because of that, again there will be shrinkage, that is called as autogenous shrinkage. Okay. In addition to that, we also have something called carbonation shrinkage. When your concrete is subjected to CO2, higher CO2 environment, then the calcium hydroxide that is in the concrete can react with CO2 and create again additional shrinkage, which is called as carbonation shrinkage. But usually it is considered to be a less effect than drain shrinkage and autogenous shrinkage. So what we do is we add these two effects, drain shrinkage value and autogenous shrinkage, to get your total shrinkage. Right. So this some of the uh, previous work, it tells what is the effect. Okay, we are considering two scenario. Again, in the x-axis you have time, and in the y-axis you have basically swelling and shrinkage. Swelling is on the positive axis, and then shrinkage is on the below this thing. So we are considering actually two specimens. One specimen which is stored in water, which is always stored in water. That means you're not allowing the water to go out of the system, because it's always uh, it's stored in water. Now the another specimen, it is stored in air. That means it is allowed to dry. So you can see here that it is going to shrink over a period of time. So because of shrinking, you're going to develop some shrinkage strain. Now again, when you do alternate wetting and drying, so when you do again wetting, then this shrinkage will reduce. Then when you dry, again shrinkage will increase. Again when you do wetting, so this cycle you keep doing, so it will keep going. Okay, right? So this is what alternate wetting and drying. So this is because of the moisture movement in the concrete. Now let's see what is the effect of curing on shrinkage. Now we are looking at again the same on the below this axis you have shrinkage, which is given in negative values, and the above values are given as swelling. Okay, and we are looking at different scenarios for specimens with a water cement ratio of 0.45. The above case, these ones are basically sealed. That means, I wrap the specimens and I am preventing the escape of your moisture to go out of the system. Now, these are again, they are cured for 7 days, water cured for 7 days, and then they left to dry. So again, these are three samples we are looking at: one with water cementation of 0.35, another one with 0.3, another one with 0.45. Another one, absolutely there was no curing. It is allowed to dry right from day one, of the time of the casting. So you see here, if you're not doing the water curing, of course, the shrinkage strains are very high. It reaches a value of about 400 microstrains. However, even if you do initial water curing for 7 days, you can see that there is a reduction in the amount of shrinkage. Even that reduction is going to be higher when you have a higher water cement ratio. So that means when you have a lesser water cement ratio, again shrinkage strains are going to be less. For example, 0.35, it reaches about 250 microstrain. However, 0.45, it reaches a value of about 300 microstrains. And you can see here the sealed specimens, because you're not allowing the moisture or water to escape out of the system, you can see that pretty much they remain same. There is no change between the water cement ratios. So it clearly says that, yeah, if you cure the concrete well, again you can reduce the shrinkage strain. Now, this is another study from this literature. You can see what is the effect of drying shrinkage on the y-axis in terms of percentage. Okay, and what we are seeing is in the x-axis with respect to time in weeks. Okay, and you have specimens which are made with 307 kg per meter cube, and they were all two specimens. They were all, both of them were 7-day moist cured. But we are here. We are what we are seeing is the effect of temperature. The one was cured at a temperature of 4 degrees centigrade. Another one was cured at 23 degrees centigrade. You can see higher the effect of temperature, again higher will be the effect of your drying shrinkage. So higher the temperature, higher will be your drying shrinkage. Now, again, we talked about this. The major constants that affects the shrinkage are water content, type of cement, type of aggregates, and use of mineral admixtures. Of course, if you use a lot of mineral admixtures, we can improve the durability. We talked about that. And again, aggregates are inert material, and they are stiffer elements in the concrete for concrete of strength in the order of up to 50 megapascal. Usually, the aggregates are stiffer and stronger than the cement paste. So, if you have a stiffer element in the concrete, again, it will prevent the cement paste from or restrain that. So, it will reduce the amount of shrinkage. So, that is what it is. Here, we are seeing the effect of drying shrinkage with increasing water content for the same type of concrete. Higher, you can see clearly that the shrinkage is increasing with increasing water that you're using in your mix design. So, so the drying shrinkage for reinforced concrete is expected to be lower than what you have for plain concrete, because again the reinforcement will help little bit in preventing that, reducing that shrinkage. Steel reinforcement actually restricts, but it cannot prevent the drain completely, prevent the drain, but however it will restrict the drain shrinkage, and drain shrinkage will increase with increasing water content. That's what we are seeing here. Okay, so if you want to reduce the effect of creep and shrinkage, the one way is to use lower water cement ratio and cure the concrete well, and also you load it at a later stage after the hydration process is sufficiently achieved. Again, this is another thing we are talking about. What is the effect of size and shape of concrete? So here we have different specimens with different volume to surface area. Okay, so so if you are increasing your volume to surface area, you can see here that your shrinkage is going to be lesser. So that means for a constant volume, if I am having a large for volume to surface area, if it is for example green color, if you see here, here we are talking about a 1000 millimeter wall. If you are having a 500 mm V by S value volume to surface area, you see here that percentage of shrinkage that is going to be lesser. So, but if your V by S values are lower, for example 38 mm, you see here, you are going to have larger shrinkage. That means if you have a larger surface area which has a possibility, or it is giving the passage for the water or moisture to escape out of the system, then you will have more shrinkage. So that is what we are trying to say here. For specimens with higher volume to surface ratios, larger elements generally experience lower shrinkage. For however, for a particular volume, if you have a large surface area, then your shrinkage is going to be higher. Okay, so the rate and ultimate amount of shrinkage are usually smaller for large masses of concrete. That is what we are seeing here. For however, the shrinkage will continue for a very long time for large masses. So that is what again it is also seen here. This chart actually shows with respect to time how the shrinkage strain in millions. Okay, how is it going to how is it varying for different types of specimens? For example, these are the specimens which are sealed. So you are not allowing the moisture to escape out of the system. And these are basically same set of specimens. For example, air dry specimens, they are allowed to dry at a relative humidity of about 50 percentage at a temperature about 21 degree centigrade. The only change is the size is going to keep increasing. So you are dealing with smaller specimen, which is 100 cylinder. Then we are dealing with 150 cylinder. Then we are dealing with 8-inch or 200 cylinder, and keep going. So as you can see here, if you have a large mass of concrete, again your shrinkage is lesser compared to the 100 cylinder. For a 600 cylinder, your shrinkage strains are lesser. However, it is, if you see this 100 cylinder, it nearly reaches a maximum value, and it does not increase much after say 200 days or so. However, if you're looking at 600 cylinder, you can see here that the slope keeps on increasing. So that means for large masses, though the shrinkage values are lesser, but it happens for a long period of time, so that we need to consider. Right. So now what is autogenous shrinkage? Again, autogenous shrinkage is a maximum or the macroscopic volume reduction of cement paste, mortar or concrete, which is caused by hydration process. Okay. And autogenous shrinkage develops during hardening of concrete, and major part happens in the early days of casting. And when external water is available, and autogenous shrinkage cannot occur, and autogenous shrinkage increases with decrease in water to cement ratio, and with an increase in fineness and the total amount of cementitious material that is in the system. So this is the way it varies. And usually it is in the order of 100 micro strain or so. But again, when you're dealing with high strength concrete, this number can go, and especially for ultra high strength concrete or ultra high performance concrete, autogenous shrinkage can be much higher than your drying shrinkage that we need to consider in your material aspects. Okay, now we have talked about creep and shrinkage. There is also one more shrinkage, which is plastic shrinkage. Now, plastic shrinkage refers to volume change occurring when the concrete is still fresh when before it actually hardens. Okay, and it is usually observed in the form of plastic shrinkage cracks, which occurs before or during finishing. Okay, so you can see these type of cracks. Okay, and these type of cracks, these are all plastic shrinkage crack, and it can be controlled by minimizing the surface evaporation, either through use of fogging or wind breaks, or you completely shade the casted concrete, or cover it with plastic sheet covers, or you use some spray on finishing aids. Basically they are evaporation retarders, or by using some synthetic low elastic modulus fibers. They also help to reduce this plastic shrinkage crack. Okay, there is one more shrinkage called carbonation shrinkage. So again, mainly design codes consider autogenous shrinkage and drying shrinkage, and drying shrinkage is a higher value compared to the autogenous shrinkage for the low strength concrete. However, a carbonation shrinkage also can be significant, especially when you have elements that are exposed CO2, like what is shown in this figure. So moisture present in this hardened concrete, it can react with the carbon dioxide present in the air, and it can cause carbonation shrinkage. Now, what happens is the CO2 can penetrate inside the concrete, and it can react with this calcium hydroxide, and it can form calcium carbonate and water. What is the significance of this reaction is the formation of calcium carbonate, actually it is going to reduce the pH. Initially when the pH levels are in the order of 12 and 13, basically you have this protective oxide film that is formed over the layer of steel that is going to prevent the corrosion. However, when the pH is reducing, okay, the steel corrosion can occur due to this absence of protective oxide film provided by concrete's high pH. When the pH is reducing, this protective oxide film will not be there, so it will lead to more corrosion of steel rebar. So that is also an effect of carbonation, in addition to the shrinkage that is caused. Right. So now we will talk about the temperature effects. And as you see, the concrete can expand with increase in temperature, and also it can contract when the temperature is decreased. So the seasonal variations in temperature can create a lot of internal stresses in concrete. Now, how do we do that? We how do we tackle this increase in or expansion or contraction? We have to provide these kind of expansion joints or joints so that we can limit these stresses that are created by this temperature fluctuation. And sometimes temperature stresses also develop because of temperature gradient that happens in structural elements. Because one side may be exposed to higher temperature, the other side may be exposed to low temperature. So you will develop some thermal gradient that will also create some thermal stresses. Usually, for accounting for this thermal stresses, what we do is we provide this nominal reinforcement that will, even after cracking, again the reinforcement will limit the crack widths and it will account for this additional stresses that are developed because of this thermal effect. And for the design purposes, the coefficient of thermal expansion is usually used as 6 into 10 to the power of minus 6 per degree centigrade for concrete which are made of calcareous aggregates. And it is going to be higher of 12 into 10 to the power of minus 6 per degree centigrade for concrete of siliceous aggregates. So you can see that siliceous aggregates are going to expand more, and their coefficient of thermal expansion is higher than of aggregates which are calcareous in nature. Right. So with this, I think let's summarize what we have discussed in this module 2.2. We have briefly discussed the stress strain properties of concrete, which are suggested by the IRC 112. Sorry, this should be IRC. Okay, IRC 112. And we also talked about long-term effects like creep, shrinkage, and temperature, how they're going to affect. And the factors that affect these long-term properties were discussed in detail, right? And how these long-term effects can be considered in design also, we discussed briefly. So with this, we will end this module 2.2, where we talked about long-term effects in detail. In the next module, we will talk about the properties of steel and how the design properties of steel are considered. Okay, thank you.